Good afternoon, everyone. This team is conformed by Andrés Esperanza, Miranda Vázquez, and Valeria Arguelles, and we're going to present our solution for the X-ray phantom specifically for the course of processing of medical imaging for diagnosis.
At C3M, we perform a high volume of X-rays where consistent image quality is key for diagnosis and patient care. However, most quality assurance phantoms are costly, bulky, and not adapted to modern systems. Our project proposed a low-cost modular phantom with a standardized acquisition protocol designed to improve quality assurance efficiency. We worked with the Philips BV Pulsara C-arm, commonly used in surgeries. Its mobility and advanced imaging features make it ideal for both clinical use and quality assessment. Together, these tools enhance our quality assurance process and align with real operation room needs.
Let's present the objectives, scope, and image processing approaches of our project. We designed a reproducible acquisition protocol to evaluate spatial resolution, contrast, and noise in radiographic images. We also validated these metrics against international QA standards. Finally, we applied digital processing using filters and enhancement techniques to improve image quality and achieve better CNR and SNR.
At the heart of our solution is a 3D printed phantom composed of four stacked levels, each designed to test specific imaging parameters. Level 1 contains a layer of clear gelatin, serving as the base medium for image acquisition. Level 2 incorporates the fine metallic powder scattered throughout the layer to simulate image noise and scatter effects. Level 3 includes a series of seats with precisely spaced separations ranging from 3.5 millimeters to 13 millimeters, designed to evaluate spatial resolution. Level 4 holds a set of objects with varying densities, including Mexican 5 pesos coins, a nickel coin, staples, paper clips, cardboard, and aluminum foil, to test the system's contrast resolution. This multi-level design enables a comprehensive assessment of image quality, combining noise, resolution, and contrast evaluation in a single scan.
We acquired images using the imaging modality of digital radiography, and for the digital radiography scans, we use a tube voltage of 48, 50, 54, and 56 kilovolts peak, and a source to image distance of 75 centimeters. We ensured that all Phantoms modules were captured in a single projection. Before each acquisition, we carried out a mechanical and radiation safety checks in accordance with international standards.
We analyzed the images using our MATLAB toolkit, applying processing techniques to improve clarity and measurement accuracy. For spatial resolution, we enhanced line visibility using sharpening and interpolation. To assess contrast, we calculated CNR after filtering with median and histogram equalization. Noise was measured through CNR and standard deviation along with the coefficient of variation. Overall, post processing was key to improving visual quality and metric reliability.
Here are example images. On the right, a digital radiography projection showing the contrast module. On the left, a single digital radiography that captures all three modules simultaneously, with spatial resolution, contrast, and noise model. We performed 4 replicate scans for each modality to test protocol robustness.
Now let's talk about the spatial resolution analysis. In the graph, we can see a clear inverse relationship as the spacing between lines decreases, the measured resolution increases. The maximum resolution was 0.179 lines per millimeter at 2.8 millimeter spacing, while the minimum was 0.0375 lines per millimeter at 13 millimeters. These results align with the Phantom's physical design, confirming that the system can resolve structures across a range of spatial frequencies relevant to clinical evaluation. Now that we have a baseline measurement of spatial resolution, we will apply image post-processing techniques to enhance edge clarity and contrast perception, simulating a visual improvement in resolution. After applying image enhancement through sharpening, Laplacian filtering, and bicubic interpolation, we observe a measurable improvement in image quality. The CNR increased from 3.63 to 4.48, and the SNR improved from 7.58 to 8.69. Although post-processing does not increase the system's true spatial resolution in line per millimeter, it enhances visual clarity and contrast, leading to better edge perception and noise suppression. This makes line pairs more distinguishable to the observer, but does not allow the system to resolve line pairs that were not captured initially.
First of all, we want to explain the noise reduction with the median filter. What it does is that the 3 by 3 median filter replaces each pixel with the median of its neighbors, effectively knocking out spiky noise while leaving edges intact. The effect that this has on the CNR is smoothing away high frequency noise in the gelatin background, and this drove the background standard deviation down. Since the CNR is the signal difference divided by the background noise, that alone raises every CNR, even for very subtle objects. Another thing is talking about the contrast stretching via the histogram equalization. What it does is that the equalization redistributes all the gray levels so that the originally narrow mid-gray cluster, which is where the most pixels sit, stretches to cover a much wider range. Darker objects get darker and brighter objects get brighter, and the mid-tones fan out. The effect that this has on the CNR is that larger separation between each insert's average gray value and the background mean increases the numerator of the CNR formula. In other words, foil and cardboard, which used to be almost the same shade as gelatin, now stand out sharply. The combined impact of both methods is as follows. For the high contrast inserts is that the 5 peso and nickel coins were already extremely visible with a CNR bigger than 30. They only saw a tiny boost since there was little noise or contrast left to improve. For the medium contrast inserts, the staples jumped from the CNR from 16 to 32, a doubling, because noise plummeted and edges stayed sharp. And finally, for the low contrast inserts, the cardboard left from zero point 0.9, literally invisible, to 19, and foil from 1.6 to 23, turning undetectable into easy to spot.
In this analysis, we evaluated image quality using two quantitative metrics, the signal to noise ratio and coefficient of variation. The SNR allowed us to measure how much the signal stood out from the noise, while the CV reflected the relative variability in pixel intensities. We applied different filters, including Gaussian, median, and Wiener. Also, the Gaussian filter only provided the signal to noise ratio by 0.10 decibels, but it produced the best visual result among all filters tested. And also, the coefficient of variation slightly decreased from 78.04% to 76.74% after filtering, suggesting enhanced uniformity in pixel intensity distribution. This highlights the importance of combining quantitative metrics like SNR and CV with qualitative evaluation when assessing image quality. After noise reduction, this is the visual comparison between the original and the filtered image that shows a significant reduction in background noise after applying the Gaussian filter.
In this part of the project, we built a segmentation pipeline to identify materials in the X-ray image, including coins, clips, aluminum, and cardboard. We began with K-means clustering to group pixels by grayscale intensity, providing an initial separation between materials. We then applied address holding to convert the image into a binary format and refined the segmentation using a region growing algorithm starting from seed points. This process worked well for metallic objects like coins and clips. However, cardboard could not be segmented successfully, likely due to its low contrast and intensity similarity with the background. Throughout the process, we analyzed the intensity histograms at each stage to guide our threshold choices and understand how the segmentation was evolving.
Alright, to wrap things up, we know that for spatial resolution, using our 3D printed Phantom, we measured line pair spacings down to 2.79 millimeters, equivalent to a maximum spatial resolution of 0.179 LP through millimeter. That matches or even exceeds the theoretical 1.2 to 2.9 LP through millimeter spec of the Philips BV Pulsera, so we know the system can reliably resolve fine details. For the contrast to noise ratio, after the median filtering to knock down the background noise, the CNR improvements were dramatic. The staples jumped by 94%, the cardboard by 128%, and the aluminum foil by 362%. So structures that were nearly invisible before now stand out clearly. For the signal to noise ratio and uniformity, the Gaussian filtering boosted our SNR from 4.22 decibels to 4.32 decibels, while the coefficient of variation fell from 68.04% to 66.64%, indicating a more uniform image. The key takeaway is that by combining simple and low cost filtration and histogram equalization algorithms in MATLAB without expensive toolboxes, we not only meet international QA benchmarks, but also sharply improve the visibility and critical structures. For the next steps, we could automate the scan for a simple sequence and integrate these metrics into a user friendly QA dashboard, and then extend this protocol to other Phantom designs and modality. Overall, our Phantom and processing pipeline deliver high quality, portable, and cost effective QA for CI3M's digital X ray fleet. Thank you so much.